Okay, so time to get going. Here's where we were last time. We were talking about spherical coordinates, and remember this is a different way of keeping track of where you are in space. So just a quick reminder, very quick reminder, because we went through the details last time. Theta tells you, in some sense, how far to rotate counterclockwise, as seen from above, from the positive part of the x-axis, and that defines what I like to call the theta half plane. Right? Then from that, you can talk about this next coordinate called phi, which measures this angle with the positive being understood to be in the direction of the theta half plane. Right? If you go back the other way, that's okay, but that's where phi is negative. Right? So positive toward the theta half plane, negative away from the theta half plane. And between the two of those, of course, that defines a direction. Right? These two together define a direction. And then rho, which looks a lot like a P, but very importantly, it is not a P. You cannot substitute a P in place of rho. It's a different thing, right? Rho tells you, and again, loosely speaking, but kind of how far to go in that direction, with the understanding that, again, of course, it also could be negative. So it's not a distance; it's a coordinate. So roughly speaking, how far to go in that direction, and of course, if it's negative, you just go the other way. Okay, so we talked about that last time, and that's where we ended it. So let's talk about how to convert between rectangular coordinates and spherical coordinates. In particular, if you know the spherical coordinates, how do you find the rectangular coordinates? So looking at this picture, there's a key part of this picture to make sure to focus on. In my opinion, of course, this is just my opinion, but that is this triangle that I'm going to highlight in yellow. Right there, this yellow triangle. And just for convenience of drawing, I'm going to redraw it over here, where I can see it a little better. For one thing, I made it a little bigger. For another thing, more importantly, here I'm looking straight at it. One of the problems of trying to do three-dimensional stuff on a two-dimensional screen or a two-dimensional piece of paper is that you're looking sideways at things sometimes. And right angles don't look like right angles, and it can just be very confusing, right? So anyway, this triangle reproduced here, some very simple observations about this triangle give big payoff. In particular, notice that our angle phi here is also that angle there. And then you can just think about the trigonometry of this triangle, in particular, this side. Now, coming back up to where we were, don't forget that's actually this right here. Well, that's literally the cylindrical coordinate r. That's something we've already understood. And because it's something we've already talked about, and we see where it is in this picture, and simple geometry here just tells us that that r is rho sine phi. Right? And then likewise, this right here is clearly the z-coordinate, right? That's the height in this triangle. And also, again, from this triangle, that's clearly rho cosine phi. And I claim that once you make these observations, everything else kind of falls into place. It's kind of automatic. What are the formulas for x and y? After all, well, the formulas for x and y are r cosine theta, r sine theta, just like they are in cylindrical coordinates. And we have a formula for r. Right? What is z? Well, we already know it's rho cosine phi. So very, very simple, I'm going to say memory even. It's not even a calculation, right? Gives you these proper conversion formulas, and the only real heavy lifting that went into finding these formulas is these two observations about the trigonometry of that triangle. So, for whatever it's worth, to the question of, how are you going to remember these formulas, and you must know these formulas. These are important conversion formulas. How are you going to remember them? I've never memorized these formulas ever in my life, and I've used spherical coordinates just tons and tons. Comes up a lot in physics majors. So every time I need these formulas, I think about this triangle, I make these conclusions, and then I just write down the answer, right? It's very, very easy. So I have great confidence in my ability to think through simple trigonometry. Personally, I do not have any confidence in my ability to remember rote formulas. And my lack of confidence in myself is well-founded there, right? So I advise you to strongly consider the same. Now, if you are good at memorizing formulas, okay. But I think still important, make sure you understand how these simple observations will do the heavy lifting for you. Okay. Alrighty, moving along. Real quick, a sphere. Excuse me, I got ahead of myself. Sorry, that's not a sphere. This is an easy relationship between x, y, z, and rho. Right? X squared plus y squared plus z squared is going to give you that overall distance from the origin squared. So making that observation, not hard to see, no pun intended, that this will always give you the equation of a sphere. Right? Now you can see that from plugging in the formula and saying, well, you literally get the old rectangular formula for the equation of a sphere, or, of course, you can just note that this says distance from the origin, again, loosely interpreted, is constant, and, of course, that means a sphere. Okay, so again, thus the name, that's why they call this spherical coordinates. This next example is a bit of a wild one. Let's see here. Let me zoom in a little bit more so we can see better. You'll recall that with polar coordinates, there were kind of two ways to write points in polar coordinates. In some sense, you're either going the right direction or the wrong direction with your theta. Of course, you can always go around an extra 2 pi. So to be precise, there are infinitely many. But aside from the obvious, of course, you can always add 2 pi. There's two non-obviously identical ways to write points in polar coordinates. Okay, well, that's because there's one angle that can be either exactly right or exactly wrong. Spherical coordinates has two angles, and therefore there are 4 ways to write a point in spherical coordinates. So this is geometrically challenging. I think this is a good exercise. It's a good thing to think through. I'm going to walk you through part of this example. I'm going to leave the remainder to y'all as again, a good suggested exercise to think through on your own, compare with your friends, discuss, debate. I think it's all healthy, good learning experience. So starting with this point, which is right there. You can see the x, y, and z coordinates. So we have this starting geometry. A little bit of easy trig will persuade you of what that angle is and of what that angle is, and that's just high school trig, no big. Right? I'm going to assume that y'all are good at that. And also these distances, and you can compute that distance. That's all easy geometry. Okay, so with that noted, let's talk about our spherical coordinate options. So how would I put this point into a theta half plane? And the obvious choice would be that value of theta right there, pi over 3. Previously noted, easy trig, that's pi over 3, right? Okay, well, that's true, but of course you can go around an extra half turn, right? You can add pi to that value, and so this gives us a different value of theta. This gives us the theta going in exactly the wrong direction. You can think of this purple point as being something that you can understand by way of this blue theta half plane. And that doesn't seem right. That seems kind of wrong. But let me just point out, let's get rid of the mess here. Oh, gosh. Okay, well, here I can just do that. This point, from the perspective of that value of theta, let's talk about phi. Right? What is this in relation to that blue half plane? That's just a negative value of phi. So this 4 pi over 3 for theta, and then a negative pi over 4 for phi gets you pointing in the right direction. And then the rho is the distance. Everybody on board? Now, just to mix it up, just to make it weird, here's another way that I could think of this same point in spherical coordinates. Now, keep in mind, phi equals 0 means straight up. Positive values of phi mean bending toward the theta half plane, and I'm just going to kind of keep going in that direction until I'm just for visual aid, I do kind of feel like I need to see this bottom part of that theta half plane. So until I get going exactly the wrong direction. Now, again, think through the geometry. Actually, let me draw this a little bit better. Let's see here. So, right, let's talk about what is that value of phi there. Well, first of all, it's a positive value of phi because I'm going from the positive part of the z-axis toward my chosen theta equals 4 pi over 3 half planes. We have a positive value of phi. And I know that that angle is pi over 4, and I know that this total is pi, and so, a little bit of subtraction there. This phi angle here is 3 pi over 4. Right? So that gives you, again, exactly the wrong direction, and once you know you're going exactly the wrong direction, that just tells you that the rho, the rho is just, the rho is just going to be negative. So negative value of rho, given that we're going the wrong way. That make sense? So what I've done here is I've talked you through 2 of the 4 ways to represent this point, and keep in mind there are 2 others. I've talked you through how to think about this point from the point of view of this value, sort of in some sense the exact wrong, the counterintuitive, the seemingly opposite value of theta. And now what I want y'all to do as an exercise on your own or discuss amongst groups or whatever you prefer is to think through how would you do it. What are the 2 different ways that you could do this with the seemingly natural, the more convenient, the more obvious, whatever you want to call it, pi over 3 value of theta. Okay. Yeah?
How should I know which of the 4 possibilities is the correct one?
They're all correct. There's nothing intrinsically better about any of them. Right? So take a pick. Now, what we are going to find later on when we learn, there's a method called change of variables that's going to allow us to compute something called triple integrals, and there's a whole lot of ground between now and then, right? So, but we will eventually find cause to prefer some of these over the others. I don't want to say which ones just yet. But for the moment, these are all equally legitimate. Yeah. Did I see another hand somewhere? No? Everybody's happy? Okay. All right. Okay, here's just a real quickie. I think this is a fun example, if nothing else, and it's also a nice, just in case you wanted persuasion that this is going to be useful for something. We live on planet Earth, right? We need to keep track of where we are on planet Earth, and we have a nice system for that, which is longitude and latitude, right? And I'm going to refer specifically to east longitude as being the positive, and north latitude as being the positive value of latitude arbitrarily, well, for reasons that you'll see in just a second here. Okay, so the nice thing about this is that east longitude, there it is. Now, I guess I got a little ahead of myself. Here's the Earth. I've set it up as a sphere in XYZ space. I've put the center of the Earth at the center of the axis system just for convenience. I've got the equator in the XY plane just for convenience. I've got the prime meridian in the positive part of the x-axis, again, just for convenience. And with that set up, notice east longitude is literally exactly our spherical coordinate theta. How's that for nice and convenient? Right? Lucky break. North latitude, now a little bit inconvenient here. There's north latitude. That's not what phi is. Phi is that angle. So what you see, though, is that these always add up to pi over 2. Right? North latitude and phi, right there in the picture, you can see they always add up to pi over 2, and therefore phi is this very, very easy function of north latitude. What is rho? Well, rho is the distance from the center of the Earth, which is aka the radius of the Earth, which is a little under 4,000. By the way, let me recognize, for whatever it's worth, not only is the Earth not a perfect sphere, it's actually not even just the bumpiness of the surface that makes that happen. The Earth is actually slightly pancaked, just a little bit, right? And that's because of centrifugal force and the rotation of the Earth around its axis, and it adds up to actually a substantial distance. It's something like 30 miles. I've forgotten the exact number. But the North Pole is way, way closer to the center of the Earth than the equator is. Like, again, by like 30 miles. I forget exactly. So I think that's kind of a curiosity. Related note, the point on the surface of the Earth, farthest from the center of the Earth. A lot of people mistakenly think that's the highest mountain, like Everest or K2 or whatever. No, not even close. It's in Ecuador. Somewhere in the Andes. And because Ecuador has this equatorial advantage, the Earth is just wider there than it is more northerly. So, cool fact. All right. So, spherical coordinates are easily related to longitude and latitude. And this allows for the answering of an otherwise very difficult problem. And that is, suppose you are at one location on the surface of the Earth and you want to get to another location on the surface of the Earth. What is the shortest path? Pretty big deal, if you think about it, right? You don't want to take an unnecessarily long path. If you're flying a jet, right, the fuel cost is unbelievable, and there's thousands, tens of thousands of flights per day, right? This is very, very important to understand what that shortest path is and how far is it and how do I keep track of it. Really big deal. So here's the point. No pun intended, each one of these points has a longitude and a latitude. Well known, longitude and latitude. Very easy using above to convert those into spherical coordinates. Pretty easy from the formulas on the previous page to turn those into rectangular coordinates. So you can, without too much trouble, find the rectangular coordinates, x, y, z, whatever those end up being, for these 2 points in rectangular coordinates. Once you know that, it's super easy to compute the dot product. Once you know the dot product, well, keep in mind we have this old formula that relates dot products to magnitudes and angles, and you can compute this central angle that I'm calling alpha. Right? All this comes out of just knowing longitude and latitude. Right? You compute the rectangular coordinates, compute the dot product. You know the radius of the Earth is the magnitudes here, and so, boom, you know that angle. And at this point, it's all over. But the shouting, once you know that angle, the distance that we're interested in, that's just an arc of a great circle and the length of a circular arc, old formula from geometry, it's just radius times angle, and there you go. That'll compute that shortest distance for you. Yep.
So not necessarily the shortest distance between 2 points is a line in spherical coordinates.
Say it one more time.
So not necessarily is the shortest distance between 2 points a straight line.
I hear what you're saying. Now, it remains that the shortest distance is the straight line that burrows under the surface of the Earth and goes through the magma. It's not good for travel, right? But that is still the shortest distance. So we're answering a different question here. We're answering, of all paths on the surface of the Earth, which one is the shortest? So that is never a straight line because there are no straight lines on spheres. And so, yeah, it becomes a nastier problem. Yeah, that's right. Yeah. Okay. All right, so I think this is a cool little example. And by the way, think for your own entertainment, if nothing else, how else? What would be your other method to figure out what that shortest distance is without using this trick? And I think you're going to find that is actually really hard to figure out. Okay, moving along. Again, converting, one way to the other. I mean, this is morally equivalent to an example we saw with polar coordinates. If you have the rectangular equation and you want to convert into the spherical equation, it's a pretty straightforward process. You just plug in the conversion formulas. I think it's a good idea to go ahead and square out a squared term like that first, right? And if you do that first, then notice that there's a kind of a nice little freebie that just jumps right in the boat for you. There you go. You can rewrite x squared plus y squared plus z squared as rho squared. Everything else is literally just a matter of plugging in known formulas, right? So there you go. Of course, these ones cancel. That's handy. And then nice punchline. You can just solve for rho in this equation. And there's the spherical equation for that initial offset sphere. Okay. All right. Okay. So, question. Go ahead.
Yeah, for that equation up there, the x squared plus y squared, etc. I know for a circle, normally like the constant that it's equal to, like the square root of it is the radius, right? So in this case,
yeah, well that's right. So looking at this right here, you're quite right. This is the radius squared. Absolutely.
I see.
Yep.
That still holds for a sphere.
One more time.
I said that still holds for.
Yep. Yep. Absolutely. That's right. So what you have here is this is a sphere of radius square root of 1, right, and whose center is at 1, 0, 0 in space. That's right. Yeah. All righty. So moving along, y'all may have noticed I've got a great big X through a bunch of stuff on this next couple of pages. These discussions just take a little bit of time, and it's not going to come up in this course. So I want you to be aware of what I'm about to cross out. It's important to know that these things exist, and you may see them in other contexts. I'm not going to use them in this course at all. So in particular then, y'all do know the rectangular standard basis vectors. This is old news, right? This is dates back to linear algebra. Right? So you may have seen previously IJK as the notation. I've already commented how I prefer this notation just for the consistency. When you have higher dimensions, it's just easier to work with. So the point to these is that these point, there's different ways to say it, but these point in directions where, for example, this vector, if you're there, always points in the direction where one of the coordinates is increasing and the other two coordinates are being held constant. Right? Okay. Well, you can do something along those same lines in, let's say, polar coordinates. Right? So if I'm sitting at this point right here, and if I ask which direction is the unit vector where r is increasing but theta stays constant? Well, it's that direction right there, and a little bit of geometry, a little bit of vector geometry. You can persuade yourself that that's the formula. I need to move this out of the way so I don't trip on this. Sorry about that. Okay. Likewise, now, different geometric argument, but this direction right here is the direction you would go if you wanted theta to increase, but for r to, at least at the instant that you're at this point, for r to be staying constant instantaneously. Right? So these are called the polar standard basis vectors. And a couple of disappointments that they deliver. They don't play nice linear combination games with coordinates and coefficients. They just don't work very well for that. Even worse, notice they aren't even constant. Right? The E sub r vector is a different vector if you're there versus if you're here. So they're a little bit weird, but they have their uses. Again, I'm not gonna be using them in this class. Okay, so if you're looking for a little mathematical weightlifting, think about these vectors and think about how to represent them algebraically. Here's some answers to aim for, right? And see if you can make sense out of this. But again, you're not obligated. It's not officially part of the course. And again, here's some disappointments about them that you don't technically need to worry about. Okay, all right. So we move on now to chapter 2. All right. So there's a few things we have to kind of get out of the way, some terminology, some basic observations about what functions are and stuff. And then but this is going to take a little bit of time, by the way. It's a little bit boring. This will kind of make you reconsider, though, some of the things that you may have thought you fully understood about what is a function, etc. What is it? What is the inverse of a function? Right. So I'm going to challenge some of those ideas, possibly depending on your previous exposure. But this stuff just kind of has to get said. So here we go. Let's talk about what a function is. A lot of people mistakenly think that a function is a formula. That's not accurate. That's not what a function is. Very often, formulas are an important part of a function, but not necessarily, and it's not the whole story. Okay, so what is a function? A function is a trio. It's these three things. It is a domain, namely the set where the function's inputs are allowed to come from. What I like to call the target. Some people prefer codomain. It seems like an unnatural word to me. Anyway, the target, that is where the outputs from the function go into, where they must go into. And what I'm going to call the rule of assignment. Now, again, this is where a lot of people would say it's the formula. It doesn't have to be a formula. It doesn't have to be an algebraic expression. It could be. Very often, the ones we experience will be, but it doesn't have to be. All right, and one of the important things about the rule of assignment is you get exactly one output from the target for every input from the domain. So there's no such thing as a multi-valued function. That's not what a function is. Yes?
So is codomain
yeah.
Range, basically?
Yeah, well, it's close. Yeah, I'm not. The word range to me is a ruined word, because it means different things to different people. So I'm gonna say some more about that in a couple minutes.
Okay.
Yeah. Right. Okay. So let me show you some examples. Natural log. Y'all know natural log, right? There's a domain. That's the open interval from 0 to infinity. This is important. You can't talk about natural log of a negative number. It's not a thing. Until you start doing complex analysis, and some really nasty, sticky wickets have to be dealt with. In this context, there is no natural log of negative numbers. Okay. All right, so that's the domain, basically the positive real numbers. Here's the target. Namely, when I take a natural log of a number from this domain. What comes out will always be a real number. Again, we're not doing any complex analysis in this class, so log of positive number, always a real number. And then there's the rule of assignment, and that is what is the formula, and, well, log, and how do you define natural log? Well, pick your favorite textbook, and there's different definitions that are all equivalent, and I don't want to review single variable calculus. Okay, now here's another one. Oh, I should say before I go on, this example shows a notation that I think is extremely useful. It's very convenient. It's everywhere in math above a certain level. It's very standard, so I think you should know it. And that is that what goes here is the domain. What goes here is the target. And the arrow represents the action of the function taking something out of the domain and plopping it down somewhere in the target. Yeah, it's very handy. Okay. All right, here's another function. That's a function. Reminder, we have a domain. That's where the inputs come from. We have a target. That's where the outputs go into. We have a rule of assignment. And that is for every element of the domain, namely for every student, let's say at Duke, right? For every student, the rule is, what is that student's ID number? Right? And notice, of course, ID numbers are always integers, in my experience anyway. So for every input, namely every student, there is a corresponding output, namely an integer that is that ID number. So this is a function. Notice the absence of a formula. There's no algebra in here. Perfectly good as a function, no formula. All right, now just to emphasize how important this is, that a function is a trio. A function is all three of these things. A function is not just, well, a formula and then the domain and the target, whatever, who cares? It doesn't make any difference, right? That absolutely does. As follows. It may seem like fussy silliness, but these three functions right here are different functions, even though that these functions, they all have the same rule of assignment, right? F, G, and H. They all say, hey, whatever student we're talking about, give me their ID number. These are different functions. For one thing, notice these two functions here have different targets. Now, is that okay? Are you allowed to do that? Well, sure, because the student ID number will indeed always be an integer. That makes this okay. And the student ID number will also always be a real number. This is excessively broad. It'll also be an integer, right? So why are we going to allow all real numbers? I don't know. There may be some context where I need the target to be all of R, right? Point is, different functions because they're different trios because they have different targets. Okay. All right. Likewise, these two functions here are different because they have different domains, right? I can talk about a function defined for all students at Duke. I can also talk about the student ID function defined just for students in this class. Okay. All right. Now, I know that seems fussy. All right. Yeah, so let's talk about this word, image. Let's start with image. The image of a function is the set of actual outputs, not to be confused with the target, which is the set of allowable outputs. Right? Now, just as an example, here's a perfectly good function. Easy function, real numbers in, real numbers out. The function takes whatever you give me and squares it. Perfectly simple function, no problem. The target is the entire real number line. The image, and keeping in mind now, the image is what actually comes out. What actually comes out of a squaring function. When you square numbers, what comes out is just non-negatives. Right? So, importantly, this is the distinction then between a target and an image. Does everybody see that distinction? Okay. So now let's talk about the word range. The word range, depending on which book you're reading or who you ask, some people like to use the word range to mean target. Some people like to use the word range to mean image. That word range means different things to different people. Not cool, right? To me, I mean, this is we have to all agree. If we're going to have a precise conversation about important ideas where subtleties matter, we cannot have confusion over what a word means. And so my solution to this circumstance is that I just never use this word anymore, other than to explain that I never use this word. Because I don't know what my listener will assume I meant by it. But I think image is pretty universally understood and agreed upon, and I think target is pretty universally agreed upon. So I advise you use those words, and I advise you steer clear of the word range, yeah?
So this is saying that, like, the domain is all real numbers, and
Yep.
then the codomain or the target is also all real numbers.
Correct.
But then, I guess, like, how can you say that it's all real numbers when, like, I don't really see the distinction between the image and the target.
Right. So now I bet hopefully I presume that you're comfortable with the idea of looking at the set of the actual outputs.
Yeah,
that's perfectly, of course that's going to be a thing, right?
That makes sense to me, but I'm like, why would negatives be included in the...
The only requirement for a target is that all of the outputs must be elements of the target. There's no requirement that it has to be tight, right? Now, why would we allow such sloppiness? Right? Well, if I give you a wacky formula to be my function, it might actually be a significant amount of effort to find what the actual image is, right? If I give you a quintic polynomial and ask, well, that's a bad choice. Let's a quartic polynomial, right? And if I ask you to find the minimum value to be the lower bound of my image, that might be loads of work that you just don't need and don't want, don't care about, and it's got nothing to do with your interest in the function. So it's nice to just be able to say, look, I don't know the actual image of this quartic, but real numbers are what comes out, and I just need to know that they're real numbers so I can do real number stuff with them. That's it. So it's a convenience.
So all the values of the image are in the target, but not all the values of the target are in the image.
Correct.
Okay,
Correct.
that
That's right. Exactly. All right. Now a little bit more lingo. When you have a function, right, that takes an input and gives an output, what comes out? This output is, we also use the word image. I mean, just like the image set, this involves outputs, right? But this is the image of a single input point. So the output of a single input is just the image of that input. Likewise, just to flip it around, sometimes I want to know what input gave rise to that output. We call that a pre-image because it came before the image. Does that make sense to everybody? It's just lingo, right? It's convenience, but I think it's pretty natural. Yeah.
So would pre-image correspond to domain, and then image would respond?
Yes, the pre-image is always in the domain, and an image is always in the target. That's right. Yeah. Okay. Now you'll notice I put here a pre-image. Let's recognize there might be more than one pre-image. And there's only one image. For a given input, there will only be one image. Functions can only have one output. But you might have several inputs that give the same output. Right? So in order to deal with this and related complications, we have a little bit more lingo. And y'all can read through all the details here, but I just want to point out, for example, let's think about this point here in relation to this function that I have drawn sort of symbolically. Right? That output has two pre-images, both of these points in green land on that same output. So each of these individually is a pre-image for that point in the target. Okay. By contrast, looking at this function, right? Looking at this point in the target, this point in the target has no pre-images, not a one. Nothing lands on that output point. That would be that, that hopeful, that candidate output point. Nothing landed on it. This is a lonely target point. Okay. So this kind of thing happens. You might have multiple pre-images. You might have more than one pre-image. You might have less than one pre-image, etc. And so functions that only do the one or the other. So if every point in the target has at least one pre-image, we say that is an onto function, otherwise known as a surjective function, such as this example right here. You can see every point in the every point in the target has indeed at least one pre-image. Okay, and now on the other hand, sometimes, conveniently, every point in the target will have no more than one pre-image. For example, this one, right? This function right here. That point has one pre-image. That has one. That has one. That has zero. None of the points in the target have multiple pre-images. We call these functions injective, or sometimes they use the term one-to-one, which I think is unfortunate. One-to-one makes it look like it's a perfect pair. Just the language, it just looks like it's saying both injective and surjective, and it's not. So I cringe every time I say the word one-to-one because it's misleading. So you might find yourself preferring these terms, injective and surjective. Sometimes you have a function that's both, right? Missed. Sometimes you have a function that's both surjective and injective. Every point in this target has at least one, and every point in this target has at most one. Because every point in this target has exactly one pre-image. So that is both injective and surjective. It's both of the jectives, and so we use the term bijective. Natural terminology. Okay, so why would we care about all this nonsense? And the big idea here is that if you have a function that is bijective, that function is invertible. I can talk about the inverse of this function. The inverse of this function is pretty easy to draw a picture of. This point goes there, and this point goes there, and this point goes there. You just turn all the arrows around backwards. Boom! You got yourself an inverse function. Notice you can't do that in any of these other pictures. If I tried to invert there, where would the inverse send that point? Well, I've got two candidates. How would I pick? Not obvious. This is not invertible as drawn, right? For that reason. Likewise, where would I send this point here? It doesn't have any pre-images for me to choose from. Not invertible. Okay. So here's a couple of examples, and I'm going to go quickly through these examples because I think it's pretty straightforward. A lot of people mistakenly think that the squared function has an inverse known as the square root function, and that is not true. That function is not invertible. 25 has multiple pre-images. Right? 5 and negative 5. To talk about an inverse function, the inverse has to be a function. There has to be exactly one output. Doesn't satisfy the rule. So that's not invertible. But this is easily adjusted. We take, you'll notice here, the exact same formula, right? But we just play with the domain and the target, and this problem goes away. If I consider the squaring function as something to be done only to non-negative real numbers, to always produce be understood to produce only non-negative real numbers. This is invertible. Any output, any point in the target, in other words, any non-negative real number is, in fact, the square of exactly one positive, non-negative real number. So that's invertible. And being as it is invertible, we can talk about its inverse, and that is the inverse. So that's the definition of square root. Notice it is not an inverse of the broadly understood squaring function. Yeah?
So for all invertible functions, is the target of the function the domain of the inverse?
No. It's for example, the next one that we're going to look at. Let's look at this function right here. This is what I like to call the invertible sine function. It takes these angles, right, and it gives as outputs these what I'm going to call y values. Right? So notice these are different sets. Right? But for every one of those green angles, you get exactly one blue y coordinate. And by the way, I if you find it convenient, I certainly do. I find it easier to understand this by thinking of the angles on the unit circle and thinking of the y values as literally being the y coordinates, because after all, this is how we define the sine function in the first place. Right? And drawing the graph has its moments, but in this context, since I'm not talking about slopes and stuff, right? If I just want to understand the inverse function, this is really a better way to think about how we relate angles to y values, aka the value of the sine function. So this function, as written, is invertible. Notice, in order to make this invertible, I have to restrict my domain and I have to restrict my target. Otherwise, I won't be able to define a well-defined, unambiguously defined function. Okay. All right. Okie dokie. The rest of this page I'm going to mostly skip over. This is just terminology. You can totally read this. I think it's pretty straightforward. We're just talking about when what comes out is actually a vector. Big surprise, we call this a vector-valued function. Sure, of course we do. Right? Pretty natural. And likewise, when what goes in is a bunch of input variables, multiple variables, you might say, we call this a multivariable function. So I think that's pretty natural terminology. Pretty straight read. And a quick observation, a lot of people think multivariable functions are abstract, inventions of mathematicians that don't come up in the real world. The real world, after all, you look around and you see real numbers, right? But I claim you're seeing ordered combinations of real numbers, x, y, and z, for example, right? But even if you grant that, I'll point out that the multiple input variables, they don't have to be just location. You could have longitude, latitude, altitude. These are all location. This is time. Right? So you can have several input variables, and what are we going to do at a given longitude, latitude, and altitude and time? Well, we could talk about the weather. When we talk about the weather, we talk about all sorts of stuff: temperature, barometric pressure, wind speed, humidity. There's lots more. Pull out your weather app on your phone. There's tremendous amount of information to talk about the weather. So this is a vector-valued, multivariable function, and that's just the tritest of trite water cooler conversations talking about the weather. So I hope this is persuasive. Vector-valued multivariable functions are not abstract, rare, ivory tower nonsense. It's very, very real world. And let's see how we're doing on time. Yeah, this is a pretty good place to draw the line. I'm sure I owe y'all 45 seconds, so draw the line right there. Last reminder, if you came in after I did attendance and if I therefore did not mark you present, or if you're not sure that I marked you as present, make sure to stick around, make sure that I mark you as present. Okay, see you later.